Hello everyone, welcome to ITLS Academy. Our this lecture is continuation part of evaluation of non-antibiotic antimicrobial agents, and our today's lecture is semi-solid antibacterial preparations. Okay, let's start. First of all, we will study what are semi-solid antibacterial preparations. The use of term semi-solid has been coined to embrace a group of pharmaceutical preparations known as pastes, ointments, creams, and gels. The chief feature which distinguish the first three is their viscosity, or to use a more descriptive word, their stiffness, which decreases in the order that is paste, ointment, and cream. They may consist of an intimate mixture of the active agent with either an oleaginous base or alternatively an emulsion with either water or an oleaginous substance such as a continuous phase. Gels are preparations in which the base is usually a carbohydrate polymer such as pectin, methyl cellulose, tragacanth, and sterculia gum, and water, or more rarely having a base of portion origin such as gelatin with a suitable quantity of water. More recently, polyethylene glycols and other organic polymers have been used. When formulating antibacterial preparations, it is imperative to realize that the properties of the base may seriously modify the antibacterial activity of the medicament. It is quite useless to formulate a well proven antiseptic into an otherwise elegant pharmaceutical preparation without determining if the final formulation is itself an effective antibacterial agent. Test for bacteriostatic activity. The first official test was published by the Food, Drug and Insecticide Administration of the US Department of Agriculture, in which portions of the preparation were placed on the surface of nutrient agar inoculated with Staphylococcus aureus. After incubation, the zones of inhibition, if any, around the preparation were measured. This test was modified later by incorporating 10% of horse serum in the agar to stimulate conditions in a wood, and a control consisting of unmedicated base was also used in each experiment. This test is known as the cup plate test. In addition to placing the test preparation onto sectors of seeded agar, it may be placed in a throw cut in uninoculated agar, and a test organism is streaked in a parallel lines up to the edges of the throw. Failure to grow up to 3H is indicative of inhibition. Thus, we can say that the cup plate method is useful to test several preparations or varying formulations of the same preparation against one organism under identical conditions, and the ditch plate method enables one preparation to be tested against several organisms. Test for bactericidal activity. A number of tests have been described which imitate, at least in part, the principle of the phenol coefficient test for liquid disinfectants. Culture of the test organism is mixed intimately with the semi-solid preparation, and the mixture subcultured by means of a loop into a suitable broth designated to disperse the base and neutralize the antibacterial activity of the medicament. Thus, the culture may be mixed and transferred to a hypodermic synergy surrounded by a constant temperature jacket at desired intervals. The mixture is subcultured by ejecting small volumes from the syringe nozzle into subcultural medium. A technique devised by one of the author, that is WBH, was designed to test the preparation when spread onto an infected surface. The surface of a nutrient agar plate was inoculated evenly with the test organism and incubated to produce an even surface of growth. The organism should, if still viable, grow through the back of the agar disc to give growth in the subculture tube also. Next is test on skin. It is possible to also test semi-solid antibacterial preparations on the skin itself as described for liquid disinfectants. Portion of the skin, the back of the fingers between the joints is a useful spot and it is treated with the test organism and the preparation is then applied and after a suitable interval the area is swabbed and the swab incubation in a suitable medium carried out. Alternatively, the method employing pig skin may well be adapted to the problem of testing semi solid skin disinfectants. General conclusions. It is suggested that as a minimum routine for the final test of an alleged antibacterial semi solid formulation, the following be used. First is the cup plate technique for bacteriostatic activity. Second is a test for bactericidal activity. And third point is a skin test. Here, one thing, bacteriostatic is a phenomena that doesn't kill bacteria while it stops or inhibits the growth or reproduction of bacteria, while in the case of bactericidal activity this is a phenomena that kills the bacteria. So, this is the basic difference between bacteriostatic and bactericidal activity, and we have also covered all these activities in our previous lecture. If you have not watched, you must go to the previous lecture and you should watch the bacteriostatic and bactericidal activity. And the third test is a skin test. For routine assessment of test formulations during development work, the cup plate and dish plate methods are adequate, and both of these methods we have also covered in our previous lectures. Next is evaluation of air disinfectants. One of the most potent routes for transmission of bacterial disease is via the air. As we know, in our environment, a lot of microorganism is present, and mostly we can say that bacteria are most abundant infectious particles in the air. So, this is the most potent route for transmission of bacterial disease. Cross infections in hospital wards and infection in operating theaters, the transmission of disease in closed spaces such as cinemas and other places of assembly, in the wardrooms and crew's quarters of ships, and in submarines, all are well known sources. Of equal importance is the provision of bacteria free environment for aseptic manipulations generally. Clearly, the disinfection of atmosphere is a worthwhile field of study, and do this each much research has been done. It is equally clearly important to be able to evaluate preparations claimed to be air disinfectants. Heretofore, the milieu on or in which the disinfectant has been required to act as has been either solid or liquid. Now, antibacterial action in the gas or vapor phase, or in the form of aerosol, that is a colloid and is a mixture of gases and solid particles present in the air. It is aerosol is a colloidal particle interaction must be considered, and this presents the problem of determining the viable airborne population. Now come to the point, determination of viable airborne microorganism. The simplest way of assessing the viable microbial population of the air is to expose petri dishes contaminating a solid nutrient medium to the air, followed by incubation. Indeed, this method was used in 1881 by Koch. Although this method does depends on the organism or organism bearing particles actually falling on the plate by gravity. It is a method which is still used to assess the general cleanliness of air in pharmaceutical factories where aseptic operations are taking place, in food processing areas, or in hospital wards. More positive data may be obtained, however, if a force other than gravity is used to collect airborne particles. An early attempt at quantification consisted of placing a petri dish containing a nutrient agar in box beneath an inverted funnel, the stem of which passed out of the box into the atmosphere. By applying a partial vacuum to the box, air was drawn in through the stem of the funnel and impregnated on the agar. Now the plate could be incubated directly and developing colonies counted, provided the air drawn in was metered. A direct quantitative assessment of the viable airborne population could be made. The arrangement is set so that the the slit runs parallel to a radius of the dish but leaves a clear space around the circumference and the center of the plate. In operation, a vacuum is applied to the chamber containing the turnable air passes in through the slit and the nutrient medium evolves so that the airborne particles, if any, are trapped onto the medium and spread in a sector over the medium. Now come to the point that is experimental evaluations. In brief, the experimental technique is to create a bacterial population in a closed chamber. That is something like this. This is a closed chamber and bacterial population is grown inside this chamber. Obtain a quantitative assessment of the viable airborne bacterial population by means of a suitable sampling device. Now submit the population to the disinfectant action, whether it may be ultraviolet light, that is UV rays, or chemical vapor or aerosol, that is particles of gases and solids in the air, and then determine the airborne population at suitable intervals. Now come to the point that is preservatives. We will discuss that what are the preservatives and how they work. Preservatives may include disinfectant and antiseptic chemicals, although sometimes disinfectants, antiseptics, and preservatives are means only one thing. Together with certain compounds used almost exclusively as preservatives. They are added to many industrial, including pharmaceutical products, which may be, by their nature, support the growth of bacteria and molds, causing spoilage of the product and possibly infection of the user. In the field of pharmaceutical preservation, addition of an inhibitory substance to a multi-dose injection or the prevention of growth in aqueous suspension or drugs intended for oral administrations are prime example. These are some of the examples of pharmaceutical preservations. Preservatives are widely employed in cosmetic preservation for lotions, creams, and shampoos. All of these compounds contain preservatives. Preservation is also an important aspect of formulation in emulsion paints and cutting fluids, that is, fluids used to cool and lubricate lathe and drilling tools. There should be preservation of these all things also. Our next section is evaluation of preservatives. Potential chemical preservatives may be evaluated in the first place by the methods outlined above, that is, we have discussed in our previous slide, especially by determining MIC value or by viral counts. As we have studied RW and CM test and also KS test in our previous lecture, these the RW, CM and KS test have no relevance in preservative evaluation. It be recalled that formula ingredients may reduce the efficiency of a preservative which has shown up well in conventional tests using culture media as the suspending fluid. Emulsions, especially oil in water, as aerosol was the composition of air, water in gas and water in air, like that emulsion is especially oil in water composition. Emulsions which incidentally figure widely in cosmetic products are especially prone to failure because the preservatives may partition into the oily phase of the emulsion while contaminants will flourish in the aqueous phase, now deprived of preservative by partitioning. It happens sometimes that cosmetic products got bad just because this emulsion phase, that is oil in water, separates, and presence of water attracts microorganism. When the oily phase becomes separate from the water phase, then this water will attract microorganism, and finally these microorganism will destroy the cosmetic product. The cardinal requirement, therefore, for preservative efficacy is the evaluation of the finally preserved operations, that is, preparations, and this may be performed by means of a challenge test. In essence, the hopefully preserved product is deliberately inoculated, that is challenged with suitable test organism and incubated and examined to see if the inoculum has been able to grow or if its growth has been successfully suppressed. Different performance criteria are laid down for injectable and ophthalmic preparations, topical preparations, and oral liquid preparations. Inhibition of the challenge organism is determined by vival counting technique. The British Pharmacopoeia should be consulted for full details of the experimental procedure to be used. Preservative combinations. The use of preservative combinations may be used to extend the range and spectrum of preservation. Thus, in the series of alkyl esters of 4-hydroxybenzoic beta hydroxybenzoic acid, that is parabenz, water solubility decreases in the order, that is methyl, ethyl, propyl, and butyl esters. This water solubility will be more for methyl, then ethyl, then propyl, and then butyl esters. By combining these products is possible to achieve a situation where both the aqueous and oil phase of an emulsion are protected. Combinations may also be used to extend the spectrum of a preservative system. Thus, the preservative Germol 115 has an essentially antibacterial activity and very low, if not zero, antifungal activity also. That is, a preservative Girmal 115 has an essentially antibacterial activity and sometimes it also have antifungal activity. By combining Girmal 115 with parabens which possess antifungal activity, we know that this Germal 115 have antibacterial activity and this parabens this have antifungal activity. So now, with the combination of these two drugs, a broader spectrum preservative system is obtained because this is antibacterial and this is antifungal. After combination of these two drugs, there will be a broader range of the action of the newly formed drug. So we can say that this combination will have a broader spectrum preservative system. Synergy in preservative combinations. Very occasionally, a combination of antimicrobial agents exhibits synergy. Synergy is measured against a single microorganism. That is, it is a process which is applied against only one microorganism and not applied on the group of microorganism and exhibited when a combination of two compounds exerts a greater inhibitory effect that could be expected from a simple additive effect of the two compounds in the mixture. We can say that synergy is a procedure in which two drugs are combined and finally they act on a broad range of spectrum. This can be seen by that is a drug Girmal 112, 115 and paraben, which we have discussed in our early slide. These two, that is antibacterial and this is antifungal, when these two are combined, their synergistic effect becomes a broad range spectrum. So this is the process which is known as synergy in preservative combinations. Evaluation of synergy. Synergy may be evaluated and displayed by preparing mixtures of the two compounds. As we discussed, that synergy is a process in which two compounds are mixed, being investigated and determining their growth inhibitory power by means of an MIC determination. The results obtained by the evaluation of synergy may be plotted in a graph. Growth inhibition is obtained with a lower total quantity of preservative. When this becomes a combination of two drugs, this becomes a broad range antibiotic, and now the growth inhibition with a lower total quantity of preservation is obtained. That is, after the combination, this becomes a broad range antibiotic, and now this can work against a broad range of spectrum, and now its even lower dose can affect a huge population. Synergy has been discussed in depth by Denier et al. In 1985 and Hodges and Hanlon in 1991. Rapid methods. In many cases, especially in the food industry, it would be very useful if the performance of a biocide or the extent of contamination of product, apparatus, and working surfaces could be deduced sooner than that provided by a method which depends on visible microbial growth. Many methods have been devised to secure more rapid results and have been designed rapid tests. They have recently been reviewed by Denier in the 1990s. Two such methods will be mentioned here. That is, first one is epifluorescence and the second one is bioluminescence. As we know that fluorescence is a phenomena in which any product we can take it as a radioactive product, it shows fluorescence, it glows, and it is any chemical or any compound, while bioluminescence, in this bioluminescence, any organism shows luminescence, that is fluorescence or glow of light. So let's discuss these two methods in detail. First is epifluorescence. Epifluorescence depends on the fact that certain dyes like acridine orange being widely used will stain cellular materials. Some of the dyes like acridine orange and many other dyes are present that are used to stain cellular materials. These dyes stain the components of the cells and then fluorescence is shown, that is measured. When examined in fluorescent light, any living cell present will fluoresce green or greenish yellow, whereas dead cell will appear orange to red. That is, when acridine orange is used, then live cells will show a green color, while dead cells will show red or orange color. The method will be found in the literature under direct epifluorescent microscopy, that is DEM, and direct epifluorescent filter technique, that is DEFT. In DEM, that is direct epifluorescent microscopy, material suspected of being contaminated or a sample in which living bacteria are sought are examined directly. In DEFT, that is direct epifluorescent filter technique, the sample being examined is filtered and the residue on the filter examined as above. Our next phenomena is bioluminescence. In another method, that is luminous bacteria or bacteria not normally luminous but which have been manipulated genetically to become luminous are used. Bioluminescence is a phenomena in which any bacteria glows, and this can be This can be natural bacteria or it also can be manipulated bacteria, that is genetically modified, and bioluminescence is inserted from the outside. Their death under chemical stress or presence in hygiene studies are assessed in a sensitive light manner. There is an instrument named light meter that can measure the bioluminescence generated by any bacteria. A variant of this method depends on the fact that bacterial adenosine triphosphatase, that is ATPase, present in bacteria will catalyze the normal biological light producing reaction. It can be said that ATPase is responsible for the light producing action of the bioluminescence bacteria reaction to give detectable light in a sensitive meter, and this sensitive meter is known as light meter, and it have the ability to measure the bioluminescence or the light generated by the bioluminescent bacteria. So thank you very much guys for watching this session. This was the end of the ongoing lecture, and we will continue with some other new lecture. And guys, you can subscribe ITLS Academy on YouTube, and you can also get it on Google Play Store. Thank you very much again for watching this particular session.